So the recording has begun. You can proceed here. So since we have done this before, I'll just be fast. Just to refresh the memory, then we can go to the code. So this is the setup for principal components analysis. There are more details about it. I'll try to mention them as we go on. But basically, this is the idea. If you have many variables, in this case, let's say they are P. Sometimes it may not be possible to get much information from them because you don't know which ones are the more important variables. Some may be heavily correlated. So, and then visualizing several variables is very difficult. We can visualize comfortably up to 3 variables. If there are many, you can do pairwise scatter plots. But now beyond, when there are too many, even the scatter plots become problematic to visualize. So one way is to throw away some variables, but it's very difficult to know which ones are the right variables to throw away. The other way is to create a new set of variables, which is ordered in some sense, so that you know if you kick off some of them, you know exactly how much information you're throwing away. So how we do that is if you have a total of P variables, you create another P variables, each of them written as a linear combination of the original variables. So each of these new variables are what we call the principal components, and this is how it is set up. So the target here is to obtain these values, these coefficients, under certain conditions. The conditions will be such that these variables are ordered in the sense that the first one accounts for the highest amount of variation, and that goes in descending order. The second one accounts for the second highest, and the last one accounts for the smallest. So cumulatively, the amount of variation will be increasing as you pick on more of the variables. So because now you have been able to measure how much information each of them stores, you can pick the first few that have the amount of information you need. So there are a few problems that will arise. One is now you can no longer interpret these values well, because these variables that you use to create them may be of different units. Some may be kilograms, some may be centimeters, some may be several different units, could be distances. So it's this combination now cannot be interpreted, but all you can say is that the setup is now ordered in such a way that you have decreasing information as you go down, where information is measured by the amount of variation captured. So you gain in one way, but you lose in some other way. But if your aim is mostly prediction, you may not care so much about interpretation of the variables, but you may gain from the ordering of these new variables. But there's more detail on this. It's just that this is more a course on linear algebra, so will not give the details. So this is what I was saying. We extract those coefficients under these conditions. The variances must be ordered in this descending order, and we also insist that the variables must be uncorrelated. Same thing as covariance being equal to 0. So they are uncorrelated. I'll go back to the canvas or the border so that we can have a graphical illustration. We didn't do that last time. From a geometric perspective, we can explain this better. So I think we explained how to do this. So did I define sigma? Yeah, sigma is here, the covariance matrix. Once you get the covariance matrix of this random vector, we call it sigma. Now, there's one assumption that's usually made is that this data has been centered. So the covariance matrix is simply X transpose X, I think. Yeah. So once you have the covariance matrix, you do the eigen decomposition of the covariance matrix so that you can get this eigenvalue and eigenvector pairs. Now, these eigenvalue, eigenvector pairs are the ones that will give you these coefficients. Yeah. Each vector will be a set of coefficients for one of the transformations. So here, like the ith vector will look like this. So the ith vector in this list will be this set of coefficients for the ith variable. That is, yi will be a linear combination of the x variables with these as the coefficients. So the sum of these eigenvalues, but just to start off first, each yi, if the ith value of y as lambda I as the variance, that can be proved. For now, just accept it. And the sum of all the variances for the x variables equals the sum of the variances of these principal components if you add all of them. So you have not lost information if you use all of them, but you have ordered them in such a way that if you throw any variables, you know exactly how much information is retained. So the proportion of variance that is explained is given by this quantity. If you're picking the kth principal component, then this is the amount of information that will be retained. We'll see that in this is just how you compute the correlation between each principal component and one of the variables, xj. So this is an example we did where we started from the point where you already have a covariance matrix. Then you got these variances for each of the y variables. These are the corresponding eigenvectors. And using those values, now you can indicate how you get the new transformed values, y1 up to y3. Since we had only three variables, x1, x2, and x3, we can create only a total of 3 other principal components. So this shows if you add up the variances for this principal component, no, this is just a compute variances. So you can compute the variance using of y1 because you already know how it's expressed. Now from statistics, I think you probably will learn how to compute the variance of a sum of two random variables, of a sum of a linear combination of variables, of multiples of variables, sorry. I think that one is taught in statistics. So you just apply that same formula here, and you will get the value is 5.83, which is value of lambda 1, exactly as obtained here, 5.83. So this now just confirms that the correlation between any pair of variables, I've done it for just y1 and y2. We get it to be 0.
Excuse me.
Now it's hard, since we didn't start with the actual data, you won't know what the values of y1 and y2 are, but they should be 0. You can now test this.
Hello. Hello. Can you hear me? Hello? Hello?
Hmm?
Hello?
Yes.
Can you hear me? Hi, Molimo. I had a question. So, in other words, for us to get PCA, to say if somebody is confused in an exam or something, we just get the agent uh, values, then after that agent vectors, then the values that we get come out to say many 1, 2, and 3. So that is our one is x1, 2x2, and 3x3. And those are the ones that we substitute for our PCA on y1, y2, and y3.
Start fresh again. Uh, I'm not
I am
following
saying,
what you're
go
saying
back,
exactly.
go back, go back. I'm saying, in a
Yes.
situation where to say somebody is a bit confused and doesn't know how to go about that question given in an exam or a CAT about principal component analysis. So basically, one is supposed to look for the agent values, then through that maybe the agent vectors, then the values of the agent vectors we substitute into the y1, y2, and y3, or up to y4, depending on the size of the. You
So
get, Anna?
I think that is clearly explained here. So I don't know what you are asking.
My
It
point
is
is
right here.
this.
So what you are giving as random examples may not be very helpful. Let's work with this one in particular.
Yeah, okay, go. Songa mbele basi.
So we start with the covariance matrix. At this point, you already had the data
Yes.
and you've computed your covariance matrix.
Yes.
So this is a covariance matrix.
Yes.
We had only 3 variables, so it will just be a 3 by 3 matrix, right?
Uh-huh.
So you know what a covariance matrix is?
Yes.
Good. So this is a covariance matrix. Along the main diagonal, you have the variances of the variables. So this is the variance of x1, this is the variance of x2, and that's the variance of x3, 1, 5, and 2.
Yes.
Of the main diagonal, you have the covariances.
Yes.
Yeah. So this is just an example. They don't always look like this.
Okay.
So you can have different. So now you get you get the eigenvalues and eigenvectors of this matrix,
Mm-hmm.
right?
Yes.
So here they are. We have the eigenvalues and the corresponding eigenvectors.
Again, vectors. Yes.
Now you order this in descending order. That's how we usually do it. So the first one should be the largest. The last one should be the smallest. It should be in descending order.
Order. Yes.
Yeah. Then you order your vectors also in that manner. So now this becomes the coefficients for the transformation y1.
Yes.
So that's here exactly. You notice the x3 is missing because it has
0.
coefficient 0 here.
Yes.
You do the same for the others.
Mm-hmm.
Y2, in the second one, x1 and x2 are missing because they have coefficient 0, and x3 has coefficient 1.
Yes.
Yes. So y3 is here. Again, here x3 has coefficient 0, so it is missing there.
Okay.
So
So another question. You've said that after getting the agent values, we arrange them in order, maybe from ascending and descending. So the
not
agent
ascending or
vectors.
descending. It is one
Yeah.
order in descending order.
Okay, so the answers that we get on our agent vectors, do we do the same, Ama, now that we've substituted our lambda 1 to get V1, we don't tamper with it?
What do you mean by tamper with it?
To see hatutaiarrange tena in the order vile umesema, vile tumefanyia agent values.
What do you want to arrange?
You're the one who has said that depending on the values that we have on our agent values, the values we arrange in descending order. So my question is,
it's not depending on the values, it's the values that you get. You just arrange those ones. Yes.
So my question is, do we do the same for the agent vectors? The arranging, or Apple we don't
So
touch?
why do you want to rearrange them?
It's a question. The way why we arranging our agent values
I'm also asking a question. So why do you want to rearrange them?
Because I don't know why we are arranging the agent values then.
You see, the eigenvalues correspond to eigenvectors.
Yes.
Yes. So the order in which these ones appear, the eigenvectors,
yes,
will be in the same order as the corresponding. I mean, the eigenvalues will have the same order as the so this first one will correspond to this eigenvector.
Okay, that is what I was asking.
Now, the other thing is it's important that you review the previous work we have done.
Yes.
That's why I spent the first few weeks on theory.
Yes.
And I said it a million times. You must read the theory. Because here we are not doing anything outside the theory that we learned.
Yes.
So if you don't read that one, this one will not make sense.
Okay.
Yes. So what we are doing now is assuming that you have read the previous part.
Yeah.
If you read it, this will make sense because once you get the eigenvalues, they just put in the same order as the corresponding eigenvectors. That's what we did now in the theory.
Okay, thank you.
If you do that, then you will clean up a lot of the confusion.
Yes, nimesikia.
Yes. So it's this a lot of these things you will not understand them in one move. You have to put in the time. There's no shortcut. You really must go back and read and some of them you must read more than 3 or 4 times for them to sink. The concepts can look very simple, but just to be sure, go through the concept over and over. Don't try to skim over anything. And if you understand what was there previously, then this will all make sense. Because here, all you're dealing with is a matrix. We have learned about matrices. We have learned how to get the eigen decomposition, which is what we are doing in this second case. So the only information we have added is that now we order them in ascending order. This lambda 1, lambda 2, and lambda 3, which are the eigen values of our covariance matrix. Then these are the eigenvectors. So these eigenvectors are picked to be unit vectors. You will also notice that these vectors are orthogonal. V1 is orthogonal. If you get the dot products, you will get 0. They are orthogonal vectors. And they're also of unit length. So they're also orthonormal. Then once you get the coefficients, you just plug them into this equation. So this is the first set of equation. In this case, P is 3. So this one just is checking that the variance of the first principal component is equal to the first eigenvalue of a covariance matrix, and so on. So you can also check that the variance of the second principal component will be equal to the second. So this is possible to compute. I did not plug in the values. Variance of X2 comes from the covariance matrix. This one, I think, is cut short. I'll need to rearrange this. There's something missing on. This is incomplete. I will have to rewrite this. I think I already shared this, but once I fix it, I will reshare. but you know how to calculate the variance over sum.
Sorry,
So
sir,
this should not be a problem.
Excuse me. Hello.
Yes.
There are some people who are asking to be let into the lecture.
I think they are in now. There's no more people. So I hope that is clear how this works. So this can work for any size. I picked the case of 3 variables because it's easier to illustrate. There are situations where you have as many, in real life, you'll have as many as a million variables. But of course, that will not be done manually. But once you understand the case of 3, the idea can be extended to as many variables as there are. So this basically shows, this again just double checks that the sum of the variances. This symbol, I will change this. I think the standard way of writing the variances is usually sigma squared. But I think the book I looked at for some reason was writing them like this. I will change this so that it looks better. So these are the variances of this is the variance of x1, the variance of x2, and this is the variance of x3. They are from the covariance matrix. This is what they are, and when you add them up, they should be equal to the variances of y1, variance of y2, and variance of y3. When you add them up, they should be equal. But as you can see, the variances of the principal components are in descending order, so you can figure out if you drop out some of the components, you can know how much information you have left. So the proportion of variance explained by the first 2 principal components will simply be the sum of the these variances divided by the total variance for the components. So you can compute this and figure out what proportion this is. I did not compute it, but it seems to be substantial. The last principal component seems to account for a very minimal amount of variance. So the first 2 may be sufficient for most of your purposes. So we will see now this next one simply does exactly the same thing, but now it takes into account the different levels of variation. You may have units, some measurements that vary. You can find, let's say, for instance, some measurements may be between 0 and 4. Some variable may have those limits as their minimum and maximum, but may have others that go as in the same set that are as big as 10,000, and they bias the result because the one that has large values will its importance will be exaggerated because of the large value. So when you standardize them, simply subtract the mean and divide by the standard deviation. You get a new set of standardized variables, with each of them has mean 0 and variance 1. So once you have this new set of variables, you perform your PCA on this new set of variables, which are standardized or scaled, if you like. They're scaled now. And the idea is the same. There are a few changes in like how you compute the correlation between yi and zk. This is what it is. And then the total sum of the variances now will just be equal to the number of variables. Remember, now this Z1, each of them has variance 1. So their total variance is P, because you have 1 added to itself P times. That will also be the same for Y1, Y2, and YP, up to YP. Y1, Y2, and YP will not each have variance 1. That will be not the case, but their total will still be equal to P, the same as the variances for the standardized variable. So, but now the rest of it is the same. The only change is now, instead of working with the original variables here, you are using the standardized ones. So now the matrix we are really interested in here is this matrix V, the one that contains the eigen, what do you call them? The eigenvectors. So that's the matrix we are going to carry with us. I'll go to the board, explain a few things now. Now, this is news. I can get rid of this. You can still see my screen, eh?
Yes, we can see.
Yes.
So the setup is like this. You have a data set. This one has your variables. So X1, I'll just use 3 of them, X2 and X3. So they have values. They have several values. This they will have several measurements all the way. This one will also have several measurements. So this can now be treated as a matrix, the matrix that contains the original data. So we can assume the data has been standardized or centered. So once that is done, in any case, the standardized and centered data both have mean 0. So that makes it easier to compute the covariance matrix. So the covariance matrix will be this X transpose X. This is what we call sigma. So sigma is the one we try to get the we get the diagonalization of sigma. So this D will be the diagonal matrix whose entries are the eigenvectors of the covariance matrix, and everything of the leading diagonal will be 0. Right? So that is this matrix. And then V will be the matrix whose columns are the corresponding eigenvectors. So these are the components we need. Now we will need to transform this into the new matrix, where now we have new variables, which we'll now call Y1, Y2. They can be more than 3, but let's stop at 3 just for convenience. So again, these will be new values. I just put dots to represent them. Now these new values, in terms of the matrices we have obtained, are obtained like this. You multiply X by V. So this will give you the new set of variables. You just pick the whole matrix containing the what do you call it, the data set, and you work this out. Now you can connect this to singular value decomposition as follows. If you get the singular value decomposition of X, you get U times some matrix sigma. Sigma here is not the covariance matrix of X. So this is just the matrix with the singular values of X. And then, so this symbol is used ambiguously here because we've used it also for the covariance matrix for X. At this point, it is not. Then on this side, you'll have V transpose. So this V transpose you get from the singular value decomposition of X is the same as the V transpose you obtain here. But singular value decomposition might also assist in this product because I can now replace X with this singular value decomposition. Then I will have U sigma V transpose V, right? But I know V transpose is an orthogonal matrix. So if you multiply an orthogonal matrix by its transpose, you get the identity. So what I have here is X is equal to U sigma. This is another way of getting, no, excuse me. I've made a mistake there. We're getting Y. So what I need to have is, this is Y. The new transformed data. So the new transformed data is exactly the same shape as the old data. The only difference is now these are ordered in terms of how much information they carry. So that if you cut it off at this point, you know exactly how much information you're retaining and how much you're losing. And maybe you can live, you're willing to live with that loss. You're able to achieve your purpose with just this. So now this becomes easier to compute. This is much easier to compute than if you were to start with this. Computationally, this is much easier. You don't need to worry too much about this now. That is just for your knowledge. But this is because this will be the set of the left singular vectors, and this will be the matrix of singular values from the singular value decomposition of X. So there are two ways you can get this V. You can get it from the singular value decomposition of X. I think I may not have covered this in the slides. Or you can get it from the eigen decomposition of the covariance matrix of X. And at this point, we assume that X is either standardized or it has been centered. That is the only way now the covariance matrix will look like this because the mean is 0. Standardized or centered. So let's see how we can interpret this geometrically. So if you have, we'll work with the two-dimensional case because that's the easiest one. So if you have data, so if these are the points, I don't know whether the data looks like data. I'm just trying to draw as many dots as I can. Assume these are all dots, the points representing the XY pairs. So if you have, these are two variables, X and Y. So how principal components analysis works is it starts by finding out the direction with the maximum variance. So in this case, the direction with the maximum variance, let me change the color. So in this case, the direction with the maximum variance you can see, let me just first put some marks here. You can see in this direction, you have the highest variation, right? So that becomes your first principal component. So that vector becomes your first vector. So this corresponds to some eigenvalue. This is your first eigenvector. Then the second direction, the other direction now, which contains the most variation is that one, but it's in the next smallest variation, the next The largest was that one. Then there are only two now. So the only other one you can consider is this. Now we need this to be perpendicular, these vectors. They should be orthogonal so that their correlation is 0. So now we have a new set of axes. Instead of representing the data in this set of axes, you have a new set of axes which you can use to represent the data. So you can now rotate it. When you do the rotation, now using this red, your data now will appear along this new line. So at this point, all you have done is rotate. So you haven't changed much other than rotate. Now, the other thing you can do now is reduce dimension. So how do you reduce dimension? To reduce dimension, you simply project. So for instance, if I want to reduce dimension to 1, I will reduce it along the direction that has the most variance. In this case, it is this that has the most variance. So with that rotation, now I can reduce it to this one. But how do I do it? If I have a point here, what I will do, I'll drop it directly. So for instance, if this point was 7.5, I drop it down and I reduce it to this coordinate here is 7.0. X will not change, but Y now will become 0. So I'm now able to represent the point in just one direction. But you see, since there's not much variation in the Y-axis, by dropping all these points just to the X-axis, I only lose a little information. And then I do not need this second axis to represent them. I just now pick the new points on the X-axis. These are now become my new points, but now I have only one dimension. I've knocked off the second dimension. All the coordinates here will be 0. So now if it was in 3 dimensions, you'd have to project it onto a plane. Instead of a line, now it will be a plane. From 3, you reduce it to 2 dimensions, then it's projected onto a plane. It's harder to draw for 3 dimensions, but that's basically what happens. So that way you're able to reduce dimension. You lose some information, but now I don't lose so much by representing using this first principal component, because there's very little variation in that second principal component. In that direction, there's very little variation. So if I drop it and just present my points along this first component, then I have not lost much information. The variation, I have lost some, but not much, because there's not much variation in that direction. I don't know if that makes sense. I hope it does. So I also hope you have had time to check the data camp. What do you call it? That data camp courses on Python, for those who don't know. Because you're going to need that for this course. And you have a resource where you can learn. So for that one, make sure you take the Python courses so that you can follow. By now, you should have done some of them. If you didn't know them already, that is. So this contains some linear algebra, but okay, we can run through the linear algebra a bit, but that was not the main point for today. Some of the basics we did earlier. So this is just from the beginning, where you have some vectors, you set them up as NumPy arrays. You can get their shape. You can see these ones are one-dimensional. Only one dimension is available of length 3. You can add them. You can multiply by a scalar. So this is what is happening here. I will not, I can run this if you want. Oh, actually, I did it earlier, so the answers are here. So the first one gives you the sum of the two vectors. The second one gives you the same one of the vectors. In this case, which one is it? The vector u multiplied by 6. So this is just linear algebra from the beginning where we learned. This one gives shows you how to compute a linear combination of vectors. You have the 3 vectors. You have different linear combinations of some or all of them. This one picks vectors and confirms that it's a linearly dependent set by showing that any of the vectors can be written as a linear combination of the remaining 2. So we have this first case where we work in a 2-dimensional space, R2. And here R3, vectors from R3 that are linearly dependent. And we show what makes them linearly dependent, where every vector can be written as a linear combination of the remaining vectors. So the confirmation, once you run it, you will see the confirmation down here. This shows you how to get the dot product of 2 vectors. There's this command. You can also just do matrix multiplication to get the dot product, but then you'd have to get the transpose of u first before you multiply by v. This @ symbol is for matrix multiplication. You can still use the dot product for matrix multiplication, but it is not essentially optimized for that. So it's preferred that you use this @ symbol for when you're doing matrix multiplication instead of a dot. But both of them, if you're working with small matrices, it doesn't make a big difference. Here it shows you how to compute the magnitude of a vector, the norm. So the function that computes the norm is a numpy function, is lin np.linalg.norm. That's the one that computes the norm or the length of a vector. And some examples are here. Here we get a vector, convert it to a unit vector by simply dividing it by its magnitude. And we double check the magnitude is 1. Here is, when you run it, this is what you will see. So the distance between 2 points is just 2 vectors. P and Q is just the norm of P minus Q, which is what we are doing here. It's worked out there. Here you have 2 orthogonal vectors. You can confirm that they are orthogonal by getting their dot product, which should be 0. I will share this with you so that you can go through these basics. This one is orthonormal vectors. Again, orthonormal means they are orthonormal if they are orthogonal and also of unit length. So here we just set up an example of a pair of orthonormal vectors. And confirm that their lengths are 1 and their dot product is 0. Here is an example of an orthonormal basis and how to get the coefficients. For a given vector, you can get the coefficients of that vector with respect to the orthonormal basis easily. So this illustrates that. This will coincide with what we had done in class. So you will run through this. If you have any questions, you will ask in the next class, but it's not So this is just a function to do the same. You give it a vector plus an orthonormal basis. In this case, we picked R3, so we need 3 vectors to cover a basis for R3. Then it will compute the coordinates. So here is an example where you have a vector. I think W must have been defined up there. U1, U2, and U3 must also have been defined up there. So you apply the function at this point, and you're able to get the coordinates. What I forgot to say at this point, you see, like basically what you're doing here is changing the basis. Initially, you start with this standard basis, which are just the traditional X and Y axis. But now you change the basis. Your new basis now becomes these 2 vectors, these 2 perpendicular vectors. So you change the basis from this first set of basis to this new set. Now this new set of basis is better because it orders the new variables in terms of their importance. Where am I now? I was on the code. Let's go back there. So this one is illustrating matrix multiplication. Like I said, there are 2 ways. You could use the @ symbol. You could use the dot product as well for matrices. It works. We can. I don't want to spend too much time on that. Is it necessary to go through this that part? So this next one shows you how you can get the eigen decomposition of a matrix. So here you have a matrix A. You can set it up as a NumPy array. So it's a 2-dimensional array, this one. And then you can compute the eigenvalues and eigenvectors using this function. You can create the matrix that has the eigenvalues, the diagonal matrix with eigenvalues using this function. You can verify that Q is an orthogonal matrix. What is Q? So Q is a matrix that consists of the eigenvectors. Right? So you can confirm that if you multiply the transpose of Q by Q, you should get the identity. So if you, and you can also confirm that the decomposition works. Multiply Q by the diagonal matrix, by the transpose of Q, you should be able to recover the original matrix A. You can also, so you can now list these things and see them, the eigenvalues. Maybe I should have said print. You can print them. You can use these F strings. I think this should work, but it's better when you use F strings to print them. It's a bit slow. I think this may be the matrix we had in did we have this one in class? In the notes. So, but now here you do the eigen decomposition using this function. it gets you the eigen decomposition. So this one is done. So you have the eigenvalues. The eigenvectors is a matrix. I think the eigenvalues should be the first one, then this second. Let's see if this will be better. Something I need to check. Does this work here? Work, then it will be perfect. Let's run this again. Yeah, it is putting the line where I want it. So now it separated them. So this will be what? First line is eigenvalues. I think this will be more readable. Second one will be, I think that will be, and then the last one is simply reconstruction of A. Let's run this and see. So now at least they are labeled. Don't need this comma here. Put their label. So the first is a list of eigenvalues. The next one is eigenvectors. So this is a matrix with the eigenvectors. The eigenvectors here are listed as rows. Each of these rows is an eigenvector. So if you are to think of this as a matrix, it's actually the transpose of the matrix of eigenvectors, because each row is an eigenvector, I think. This one now is a reconstruction of a matrix A. You can see you were able to recover the original matrix, which was this one. When you try to reconstruct it using the eigen decomposition, you get exactly the I hope that will make sense. Again, here it's just the eigen decomposition, but I think this was for an example that was in the notes. So this shows you how to get the singular value decomposition. We used this in the last class where we were getting the singular value decomposition. Now here it's explained for a smaller matrix. So now we get to the highlight for the day. This is a target. We wanted to look at the principal components analysis. So we'll do this in two ways. The first one is to start from scratch. We need these packages, NumPy, the matplotlib, for plotting. And now our data set, the first data set that we'll work with is the one that comes in this sklan. I think it's also in other packages, but it's in sklan. In sklan, it splits. We will get to the splitting part. So the function we are going to construct or to write is going to be called PCA from scratch. You will give it your centered matrix X. I don't know if I do the center. Yeah, the centering is done in the function. So you don't need to just give it the original matrix and the number of components you wish to retain from your principal components. So the first thing is you center the data. So these are multi-line comments. This probably is a good thing to do for your functions to tell which arguments and explain what they are. Then what is returned as well. So it has three things to return: the transformed data, the principal components, and the explained variance ratio. So this is just subtracting the mean from the data. Then you compute the covariance matrix. This is the function for the covariance matrix. Then the next step simply gets the eigen decomposition of the covariance matrix. You get the eigenvalues and the eigenvectors. Now, this computation does not sort them naturally, so you have to do the sorting manually yourself, so that they are in the eigenvalues are in descending. Yes, they're in descending order. Then you can pick the top k eigenvectors, where that is just the same value as the number of components you put as an argument in the function. Then you can project the data onto the principal components. The components that you have picked here, you can do the projection. And then this becomes your transformed data. So this is where you multiply X by V. Remember, this principal component is the so this XV is what gives you the transformed data. So then you can compute the explained variance ratio by simply dividing the eigenvalues, which are the variances of the principal components, by the sum of all the eigenvalues. So so each of the, since they are already ordered, they will be ordered in these values will still be ordered in descending order. So the first one should give you the max, the highest variance, and so on until you get to the smallest one. Then these are the outputs. It will give you the transformed data, the principal components, that is just the matrix V, and the vector that contains the explained variance ratio. So we will load the data. So we'll use this iris data. It was data that was collected on flowers. So it's quite an old data set, but very useful for illustrating certain concepts in machine learning and statistics in general. So it was a set of 4 measurements on 3 different species of flowers. I think they were measuring the sepal length, the petal length, and then the sepal width and the petal width. So the idea was to check if these measurements can help you distinguish between the different species. So since there are 4 variables, it's difficult to draw all of them on one axis and visualize them. So we shall use this to. So once you load the data, you have to turn it pull out the data. It comes with it has a lot of information. I think it has the labels and the target data. Target names, if you want to call them labels, they're inside this object that we have loaded. But now we can pull out the data using this x.data. So this here you're just doing a scatter plot of the results. I've split it into. So there's this. The target names, they are in here. In this argument, iris.target names. This is part. This is important. It's part of the. Maybe I should try. Oh, I've been signed out. Let me sign back in. So let's try this. Spelled it wrongly. Maybe I've not loaded the data. Let's load it. Load the data. Now we were kicked out, so we have to start. All these things have to be done again. Where are we starting here? So when it kicked us out, all this was reset. So now I can load the data, then this now should work. So these are the 3 species, the target names. So they are stored in this this attribute of this object, iris, stored in there. So the names, there are 3 species: Setosa, Fascicola, and Virginica. I don't know if I pronounced that correctly. If you have some biologists, you can assist us. I think this all squarely. So this now uses some fancy function to just do a scatter plot of the data. That's all. But it is set up so that the legend makes sense. So we plot each. It's on the same set of axes, but we plot each species separately so that the legend can work well. The other ways you can do this, you could put it in a data frame and append the labels. Then you're able to plot it using the Seaborn. In Seaborn, you can easily. This is a hard way to do it because you're not working with the data frame. If you're working with a data frame, then you have some more options. This is just a NumPy array, so it's makes life a little harder. But I was avoiding Seaborn because maybe some people may not have worked with Seaborn. Work with the basics there. Seaborn is a package for plotting. So here we've done a scatter plot of just the first 2 variables. 0 and 1 is just the indices for those variables, the first 2 variables, and then color them by species. So now you can do pair plots for this so that you end up with about 6 pairs. 4 combination 2 is what, 6? The different combinations of a variable. So this one just picks the first variable and the second variable and does a scatter plot. This gives you a rough idea of what is going on. Here it seems to separate into 2 different clusters. So at this point, we have not done any analysis. We're just plotting the scatter plot of the raw data. And you can see this is what it looks like. So the values range from 4.5 to 8 for the first variable, around 2 to 4.5 for the second variable. So I suspect, I don't know which one was first, the sepal or the petal. I don't remember that, but we had petal length, petal width, and then sepal length and sepal width. So this is a pair of those. Out of those four, this is one pair. So if you want to see how the other pairs are, you simply change so this is the first and the second. So Python has 0 indexing. So the first one normally will be, we can check what does it look like if we say plot the first and the fourth one, the second and the fourth one, sorry. The fourth one should be 3. So you can see this looks a bit different. They're as a different set of variables. This one seems to sort of separate the 3 species, this set of variables. So that gives you a good idea that these variables are useful for as clustering variables, because even just as pairs, they seem to capture some clusters in the data. The first pair did not do very good capturing. It actually mixed up these two. It was able to separate these two species as one group, and this one species separately. So you can play around, because there are only 4 variables. You can play around with these values to keep changing the pairs. If it was a data frame, then it would be very easy to create a pair plot. We shall see how that works later. So this is just exploratory work. We are not doing, so far we have not done any principal components analysis. We're just exploring the data to see what can be done with it. So we run this function that we created earlier on X, and since we have 4 variables, we want to extract all the 4 principal components. So we set this up as 4. So you have the principal component here. So each row here is a vector, an eigenvector of the covariance matrix. Each row. So these are the principal components. These are the coefficients you use for transforming. So we extracted 2 things, the principal components and the explained variance ratio. So again, you can see the variance is ordered in decreasing. It seems like the first variable captures most of the variance, almost 90%. 0.92 is 92%. The rest seem not to have a lot of information. So out of the 4, you only need one variable to capture most of the information. But we shall use the first 2 so that we can plot. So here we print the transformed data. That is the XPCA. The transformed data from our function, what was it named? This one. This is the transformed data. Then this is the principal components, that's explained variance ratio. So the transformed data is this XPCA. We list the first 5 rows. And then we can get the shape of XPCA so that you see it's exactly the same shape as I think the original one was 150 with 4 variables. The transformed data has exactly the same shape. So these are the first few columns. First few rows, sorry, of the data. So that's the transformed data. Now we can plot. So this would be your Y1. We've stopped at the 5th row, but if you continued all the way, you'd have exactly 150 values for the new transformed. So this would be like your Y1, your Y2, your Y3, and your Y4, the new transformed data. So we are going to plot these first two, Y1 and Y2, because in any case, those two give us most of the variation. The first one already gives us about 92%. The second one just adds a little. And those two will be sufficient for most purposes. So I plotted this much earlier. So now if you plot along these two principal components, you can see the structure quite clearly now. You have three different clusters. You have colored them by the species. Now, principal components did not know about this species. We didn't tell it anything about this species, but it has been, because the structure exists there, it has been able to find it. It has found this structure. Now, if you didn't color these two groups, you may not be able to distinguish between these two groups here. But by coloring them, you can see they are still separated. A bit of overlap, but mostly separated. So our principal components seem to be able to pick up these clusters for the different species. Though these two, you may not be able to see them if you didn't color them by species. So that's just this PC1 and PC2 are these first two columns of the transformed data. Is that making sense? So just plot these first two. So if how you know we have plotted the first two is this one gives you the first column. This one gives you the second column. Zero is the first column, the index for the first column, and 1 is the index for the second column. And this is done for each species separately. So you start with the first species in the list, then plot its data. Then you change I becomes the second species in the list. You plot the data. Again, the reason for that is so that the legend can create itself automatically. You don't have to struggle creating the legend. But again, if it's a data frame, life is much easier. So this is now the basic idea. You've been able to reduce from 4 variables to 2. Not a big reduction here, but still good enough to be able to pick up the. So if you're doing machine learning for, say, clustering, instead of using the original 4 variables, you can choose to use maybe the first 2. So that saves you some computational time. This one is a small case, so it won't make a big difference, but it gives you the idea of what happens. You could just use the first 2, and without those first 2, you are accounting for more than 90% of the variation in the data. And if there's any structure in the data, then those first 2 will show you the structure. But now you're plotting it in 2 dimensions and still capturing the information in all the original 4 variables. I don't know if that makes sense now.
Yeah, excuse me, sir.
Yes.
I have a question. In the code you presented, which line actually shows the different color codes for the plot?
Because each plot is plotted separately. As it's being plotted, if you ask it to draw a legend, it will automatically make its own legend. So the colors are here. So when this command for legend will put a legend for each. And you can see we have, for each plot, we have a label. This label will be picked up by the legend.
And does that mean that then it will give a default color code?
Yes. You could choose to control it if you want, but I don't see the point of we will see a little later. There are cases where we have customized the colors for the legend. You will see in the upcoming examples.
Thank
So this
you.
one is, yes. So this one, we are trying to work on principal components analysis from scratch. Now, this is a poor man's option. We are going to look at the rich man's option now shortly, where you just use one simple function and it captures all this. So you don't have to work it out from scratch. The reason you do this is the idea behind the masters is to produce researchers. Researchers need to understand the nuts and bolts of everything. And that's the whole point of this first part, running it from scratch. But then we are going to run away from it and go into something more, the rich man's option, where you struggle less. Or should I also say the rich woman's option?
Yes.
Okay, yes. So for the next part, we are going to need a lot of tools here, so we'll just import all of them. I think pandas, you are aware of that. NumPy, you know it. Matplot and Seaborn for plotting. sklearn has the function for computing the principal components analysis. So we shall import that function from sklearn.decomposition. Then we will need to scale the data. So this standard scaler will do the scaling for us, what we call the standardization. You subtract the mean and divide by the standard deviation. This one will do that for us, this function. And then scipy.stats as stats. I think there's the data that we need will be in this package. We may not be using anything else from this package. I think we'll just be using only the data. Oh, I need to upload a file. I will share the file as well. So for this one, we are, no. So in this case, we'll see. I don't think we used much of this last package. I don't remember what I did, but we'll check. So I need to upload some data. I can get it from my hard disk. It's called banana. Have you seen anything called banana? So once you upload the file here, the thing is, after this session, after you finish with the session, the file will be lost. Though you can choose to store it in your Google Drive, you can still access it in your Google Drive from here. I just bring it in whenever I'm working. So we'll read the file. Since we are in the working directory, we don't need to specify any other details other than just the file name. So we'll load the file and look at the first 4 rows. Convert the group variable to a categorical variable. Look at the variances of the different variables so that we can compare them. And maybe find an easier way to look at the variances using a bar plot. So all that will be done in this one block. If I run this, that will be done. So when you run it, since I already ran it earlier, this is the output. There are 2 things we shall put out. We shall output the first 4 rows here of the data set, and then the plot of the variances of each of the, are there 13 variables? I think there were 13. So I'll try to explain the details of this data. I'll try to add those details in this script so that you can come back and download it. Initially you can download it as it is, but you can later on come back and download it after I've added as long as you have the link, you can always download it after I've added more comments. So here is the data set, the first 4 rows. Now there are several, I think this was done automatically, this unnamed, some kind of index, I think. We don't need this. Maybe I should have deleted that first. So we have this first variable for group. Now there are 4 different groups in this data set. There are actually varieties of flour made from bananas. Some the flour is made from green bananas, and the other one is made from ripe bananas. So don't ask me how that is done. I was just getting this from some book, the data. I didn't go to the details. Maybe an interesting thing to research and find out how you make flour from the ripe bananas. So we have the green bananas, but even within the green bananas, there's flour that is made from the peel of the banana and the flour that is made from the pulp of the banana. So we have the green peel and the green pulp. We have the ripe peel and the ripe pulp bananas as well. So it may be unfair to be talking about food when some have not eaten dinner yet. But you'll have to bear with that for now. So now for each of these varieties, I think there are 12 samples. So the 12 samples for the green peel, 12 samples for the ripe peel, and the same for the other 2. So a total of 48 entries. If you want to see that, of course, you can use the shape attribute of the data frame. So if you type banana.shape, you'll be able to see the shape. Then for each sample, out of the 12 samples for each variety, the following measurements are taken. We have the pH. What was this? It was total something, TSS. Something about solubility also. These are food science kind of application. So we have the pH, we have a TSS. These measurements were something to do with light, L, A, and B. I can't remember the exact details, but they had something to do with the light. So those were taken as well. Then we have, for each of the flour, these 3 variables, water holding capacity at 3 different temperatures, 40 degrees, 60 degrees, and 80 degrees were measured. So WHC is the water holding capacity for the flour. Then you have the oil holding capacity at the 3 different temperatures, 40 degrees, 60 degrees, and 80 degrees. And also they measured viscosity. And there's some way they measure texture as well. So this, I think anyone who's done food science in one form or another may be better placed to assist us with this, understanding the variables. Or someone who has done some chemistry, they might understand some of these things. But I've tried my best to explain what the variables are. I hope that makes sense. Are there any questions on the variables? So as you can see, we have many variables, about 13. Now it's difficult to get any useful information out of 13 variables by just looking at them. And it's also difficult to tell which ones are more important than the others. So we're going to use PCA to transform the data, then we see if we can get some better information. Instead of working with 13 variables, can we work with just 2 and still visualize the data? So the next one is the variances. If you look, this is what I was telling you earlier. These are the variances for each of the variables. The names of the variables are here on the x-axis. You can see there are 2 that are extremely large, way larger than the others. So if you use them as they are, their importance will be exaggerated because the variances are too high. So this is what brings about the need for scaling. If some variances are way bigger than others, then it's not, it doesn't work well for PCA. We need them to be comparable. When we standardized everything, the values now become comparable because they're all standardized to have mean 0 and standard deviation or variance 1. So are there any questions up to that point? So again, here you're exploring the data to see what it looks like. If the variances are not so different, maybe you don't need to, standardization may not be necessary, but it's just a good habit to standardize anyway. So this again is just exploratory work. This variable TSS, it had something to do with solubility. I've forgotten the details. I thought I would remember, but I can't remember. TSS was total something solubility. I may still be wrong on that. We'll double check. But now we've done a histogram of this variable TSS with the bins, with 10 bins. You can change the bins to see if it gives you any different patterns. But this one seems to give you two clusters. There's one cluster on one side, another cluster, and nothing in between here. So this may mean that this could easily mean that this variable can distinguish between two groups. One group may be the green flour, the green flour, and the other one ripe. Or maybe it may be distinguished between the flour made from the peels and flour made from the pulp. You never know. But it seems to suggest that it seems to be able to distinguish between two groups. So that is one variable. It may not have all the information you need, but this is exploratory in nature. So now you're able to see just for this variable what information it gives you about. Again, here there's no PCA yet. You're exploring the data. You can do histograms of the other variables as well and see what they look like. Maybe we should try. Which one do you propose? We can do the water holding capacity. At 80 degrees. Let's see what it does. What have I done? Oh, so I did not run this, so it has not loaded the banana. Okay, let's start from the beginning. I think I also didn't run this one. So we've run that one. Now we should have. So this is the water holding capacity. This one seems to capture almost 3 different groups. Let's increase the number of bins. Let's say the bins are 20. What will happen? When you have more bins, you capture the structure a little bit. Yeah, it seems to capture about 3 groups separately. Or are they 4 groups? I don't know. So the data here is a bit small. We have only 12 samples for each group in total. So it's the data set is small, but for our purposes, it's not a bad place to start. And then there are a number of applications where you end up with this sort of situation. You can use some bootstrapping to increase your sample size, but you learn those things in machine learning. And for now, we are not bothered so much with sample size and such issues. Our focus is applying the linear algebra. But as you play around with the variables, you're able to see if there's any structure. Like the histograms can give you a lot of information. So now we do scatter plots for each pair of variables. And I think there are 13 in total, but we've picked, if you pick all the 13, then it will be very difficult to keep track and see what's happening. So that goes to show you the usefulness of PCA, so that you don't have to struggle to keep track of so many variables. So you, here we have colored using the type of flour, whether it's from the green peel, green pulp, ripe peel, or ripe pulp. The legend, I think, is on the right-hand side if you want to identify which one it is. So some variables seem to be able to separate the different flours, others better than the others, but they all have some information about the different. Then these plots here, the kernel density plots, they also show you the distribution for each of the varieties. So therefore, they're all superimposed here. So this one, what was this? This is the one we plotted. So it actually captures 4. There were 2 separated. Let's see what they are. What are these colors? This orange one is the green peel. The blue one is the green pulp. So it seems to this total soil solubility. I can't. This solubility, this TSS thing. It's able to split between the green and the ripe. The ripe ones seem to have a higher score than the green ones on this variable only. So it seems to be able to separate those two. And even within the 2 groups, you can see one has there's like, if you focus on the ripe one, the pulp seems to score higher than the one from the peel. RPE is for peel, RPU is for pulp. Remember, this is flour. They're all flour varieties made from bananas. So you can see just from your exploratory analysis, you can pick up some patterns. We'll try to see if these are picked up also by our PCA. And some variables you can see clearly separate the 4 groups. So that tells you your variables will be good for classification. If you can see they are able to separate the groups, they are variables that pick up information about the classes. So they would be good for classification. Which one is this one? This is a light again. It's able to separate. So what does a light do? Yes, now the light separates the peels, because this blue and green are both for the flower variety made from the peels. So one is the green peel and the other one is a ripe peel. And then it separates the pulp and the peel. This one, what is it, L? It had something to do with light, I think. I will look up the details and include them in the script. I think I was in a hurry. Are there any questions on this? Is this making sense? Again, we have not done PCA yet. We are just exploring the data. So this may be something you do before you start your PCA. Try to just explore the data and see the kind of things that are in it. Is it making sense, or it's too easy? Maybe you are getting bored now. So we can get the correlation. Like we said, we normally, if some variables may be highly correlated, and that is usually bad for some analysis. Like for instance, if you're doing regression, you don't want your variables to be highly correlated. So by transforming them into uncorrelated variables, that works better for you. But by studying the correlations, you're able to tell if you have some high correlations, and you can see there are some that are high 0.92, 0.86. There's even 0.97 somewhere here. So some correlations are pretty high. Even 0.56 is it's a decent value. Even negative 0.7 is strong. Negative 0.9 is strong. There are quite a number of strong correlations. So making this a good candidate for PCA because you want to make the data uncorrelated. So this correlation is done using the heat map function. Is it the heat map? Yeah, this heat map function from Seaborn. We imported Seaborn as SNS, so we can use that to get the correlation. The other way is to get the correlation, but I think this visualization makes it easy to see what's going on. You can, using this bar, you can easily tell which ones are high and positive, which ones are large and negative. So the blue ones, as you go to the darker side of blue, you have negative values. As you go to the, is this brown or red now, or maroon? This darker side, different shades of brown as you go, or red. Not sure what to call it. They give you different. You can. These palettes can be fixed, but I don't think. If you want your own palette setup, you can customize that. You could go to. There is a whole course on visualizing data using Seaborn on DataCamp. If you go there, you'll be able to get there's the simple one, then there's the advanced one. You'll be able to see all this, how it is used. Oh, time has really gone. So I'll try to move faster now. Today we can skip the break today. So so earlier on you saw we imported a standard scalar. You have to instantiate it first. So this will be the standard scalar. This function will have.
Question?
Yes.
On the matrix table that you showed, comparing all the correlation for the matrix, is there
the
a
variables.
reason why the diagonals are all ones?
Yes, this is the correlations between each variable and itself. That will be 1.
Okay, excellent. Thank you.
So it's a perfect correlation between the variable and itself. The document is not of interest for us. This one. It's just that it was computed anyway, but it's not of any interest to us in this case. So this sets up this function that will do the scaling. So we instantiate it, and set up, call it this scalar. Then how you transform the data is you use this fit transform. You could do the fitting and the transforming separately. But here we do it at once. Fitting simply, I think, pulls out the parameters, then transform gives you the transformed data. You can do that separately. We'll see, maybe we'll see an example of that later. But here we do it all in one go. We fit and transform so that we just end up with a fitted data. The transformed data, scaled. So for the PCA, we decide to pick all the 13 components. There are 13 variables, so we've told it to look for all the 13 corresponding principal components. So we also instantiate it and call it PCA. So we are going to use this as our function for performing PCA. So we use this attribute fit, PCA.fit. It will fit the PCA onto it sort of trains our data in some sense. Then you can use whatever parameters it has trained here. Whatever it has trained, you can use it to do some predictions. We'll see an example. So pc.fit will do that for us. Then we can extract the explained variance using this attribute, explained underscore variance underscore ratio underscore. This will pull it out, and here it is. And it's in increasing order. So the first is 0.44 means the first variable. First principal component explains about 45%. Next one, second one, about 30%. So within the first two, you already have 70% of the variation explained. Then plus another 13%. So about the first three give you about 83%. The rest look rather small. So maybe they are negligible. So the first three might be sufficient for your purposes because they capture about 83% of the variation. And they might also capture some structure. So you can plot this variance as a line plot, variances as a line plot, and you can see them going down, highest being here. So this can help you determine how many principal components to retain. And usually as you go down, you stop at the point where you see a sharp turn. They call it the elbow method. So at this elbow, the elbow method would tell you that 3 components are sufficient or are a good place to stop. Where there's no more sharp drops, doesn't make sense to continue with those. So according to this, if you use the elbow method, the first 3 would be the correct. You'd say those would be the ones you want to keep. But if it's just for visualization, of course, regardless, you will pick the first 2 so that you visualize in 2 dimensions. If you want to do further analysis, maybe you'll just pick all these 3 and push them into your analysis. So another way to look at these variances, you can do the cumulative variance. This one does the cumulative variance, then plots it as a line again. So this is easier to keep track. So the first one is somewhere, no, the first 2, the first one is here. I think it had around 40 something. Was it 30 something or 40 something percent? Where is it? Around 45. So it has started from there, around 0.45 there. And the next one keeps adding. In total, you have about 70 something. And the third one captures 80 something percent. So if you want to capture about more than 80% of a variance, you need the first 3. If you want to capture more than 90%, you need to go up to the 4th. So if you are going to use the amount of variance explained, now the amount you choose will determine how the cutoff point. So if you want only 80% or at least 80%, you will need to go up to the 3rd. If 70% is good for you, I think you will need the first 2. So you can extract from this object PCA, you can extract the components. There's this attribute of components. We extract the first 3 only. There are 13, so we extract the first 3, and they're listed here. So these are the components, the first 3 rows, and so on. Each of them is these are the principal components or the coefficients of. So if you want to get the matrix V, the matrix V will consist. This will be the columns. This is the first principal component, so it will be the first column of that matrix V, the one that we use for transforming. Then this will be the second one, the second column, here it is listed as a row, but it will be the second column of the matrix V that we want. Then this will be the next component, which will be the third row of our matrix V. If you want to extract the matrix V. So if you want the matrix V, we have to get the transpose of this. So there are 13, but we stopped at the third just to save on space. So we stopped at the third here. I hope that is making sense. So the next one just shows you the shape of this matrix that contains the components. It has 30, it's 13 by 13. If you want the full matrix, it's 13 by 13. Here I've converted because here it's just a numpy array. So it's sometimes not convenient, but you have access to a few more things if you convert it to a data frame. So I've converted it to a data frame and used the variable names as the index, the variable names here as the index. So you can use this for feature extraction if you wanted to extract features. I don't know whether I should, that one you should learn that more in machine learning. But anyway, I will try to give a rough idea. So each variable, you can check the score because these are the coefficients for multiplying with x1, multiplying with x2, and so on. Up to the last one, multiplying with x13 to give you y. So these are those coefficients that you need from the ones we had in our initial setup, the model. So the values that are high, so anything that is above 0.3, I think is considered high. So the first one doesn't load very high on any particular. So it seems to be a general component. It seems to be some general measure of something. Almost all of them, they're not, it doesn't distinguish much between anything. So the second one you can see, let's look at where does it score high? It scores high on viscosity and also on this solubility. It has 0.5 here and 0.5 here. It also has 0.4 on the water holding capacity. So it seems to distinguish between two things. The water holding capacities are above 0.3, so you could consider that a bit high, but they are negative. So it maybe provide some contrast between this water holding capacity. Then the other one was what? Dissolubility and viscosity. Because the solubility and viscosity are both positive, the water holding capacity have negative values. So this may provide some contrast between those two. So the others may not have so much information, but that's how you try to extract. So now you may assign these variables that load highly on this second principal component may actually be one feature in the data. They may be describing the same feature, which you can't measure directly, but these variables loading highly on that component represents that feature. So this feature can be given a name that makes sense for the variables which are loading highly on it. So this one, I don't want to dwell too much on the feature extraction. You will learn, you should be able to, you will learn that in machine learning if you haven't already. I haven't looked at the content for the other courses that you're doing, but some of them, if not this semester, in next semester you should be able to do feature extraction and dimensionality reduction from the machine learning perspective. So this is just the loadings. The loadings are simply the same matrix V. There's nothing, it's just a big name for the matrix V, these loadings. So the other name is the scores. The scores is a transformed data. The transformed data are called scores. And now you will notice one thing. Here, where is PCA? We did the fitting first. We did not transform. We did only the fitting, PCA fit. Now, if what was I saying? So if you want to get the scores, the transform data, you need to run the transform, PCA.transform, then apply to the scaled data. We scaled the data, and after scaling it, we called it banana scaled. So to get the scores, you have to do the transform. Initially, we had just done the fitting. That one gave us the components. We didn't have the scores, so we can get the scores. The scores is now the transformed data, or this is now when you multiply your matrix, data matrix with a matrix V. So again, like I told you, this is the rich man's or rich woman's way. You just use one function and it does the transforming inbuilt function. So you have the scores and the loadings. The loadings is just the matrix V, but we have put it in a data frame. So it will be a 13 by 13 data frame. Did I set the index for this? No, it's a data frame. Then we have used some, this one is called list comprehension to create the variable names, and those will be is what you store in the columns. If you are not happy with this, you can just write it as a list of the names that you want to be for the 14 columns. But the list comprehension makes your work easier because it will construct these variables for each of the 14 variables. 13 variables, sorry. This normally doesn't take up the 14th one will not be counted. So I think you understand this loadings is just the matrix V, what we are setting up. Now, to you get the matrix V, you have to get the transpose. You observe here we have PCA components underscore to get the components, but the proper form of a matrix V is actually the transpose of each component. So that's why you have dot T. This dot T gives you the transpose, that method. So now we have the loadings and we have the scores, the new data. So here you can just put a list of the names directly of the new variables that you want. But like I said, this list comprehension makes your work easier. Someone who's been knocked out of the class. So I think if you want to learn about the list comprehensions, you can go to, I think there are some 2 courses, Python Toolbox 1 and Python Toolbox 2. They talk about some data structures in Python. I'll look for but probably you have found them by now anyway, but they show you how to work with list comprehensions. They make loops easier. Instead of writing this one can also be written as some complicated loop, but this makes the loop easier. But whatever the case, now we have the loadings, which is a matrix V, and then we have the scores. The scores is a transformed data. So it will be the same shape as the original data. And if I run this, you will see what has happened. Did I may have been logged out again. seem to have lost the, let's check. All these are working. Sometimes Google kicks me out. So let's try now. Yeah, it had, or maybe I didn't run the others. I think the output was already there, so I did not run those blocks. The cells were not run. So anyway, now we have this first one is a 13 by 13. I mean, the scores rather, they are this matrix T. The only thing we printed is we are printing the loadings first. So this first one is the loadings. So this is a matrix V. But we have printed only the first 5 rows using this head attribute. And the shape of the loading. So the shape you can see is 13 by 13. So it's there. Then the next one is the scores, which is now the transformed data. Again, we printed only the first 5 rows of the transformed data, but you can see we have 13 principal components, the same number as the variables in the original data. And then if you check the shape, it has 48 rows, the same as the original data, and 13 variables. So here, these are labels are PC1, PC2, but if you are to follow our notation, this would be your Y1, your Y2, all the way up to Y13. So this is your new data set after transformation. So if you want to do visualization, you will be doing a scatter plot of the first 2 columns of this transformed. So these first 2 columns will, but we had checked the amount of variation, and the first 2 we saw covered quite a bit. They cover close to 70-something%. So the first 2 give us a lot of information. So you see these are 48 in total. So what this does, it will plot the bar plots of all these in the first principal component. It's plotting all those. There's one other function we imported here that someone was asking about, customizing the legends. You see here, we have customized the legends. What will go into the legends? And then we put in those values here. You look at this letter and see how it works. But this one will give you custom lines with the colors that you choose. So these are, no, these are not from the, these are from the, these loadings, I think. That's correct. No, they are the scores. So we can't see all of them here, so we can't see the full range of values. I was wondering why we are seeing large values. These are just the first 5. So there are others that are bigger than this that we cannot see because you picked only the first 5 rows. So we are plotting PC1 and PC2. But now if you pick just PC1 and try to plot the values inside the first PC1 as bars, that is what this code does. Let's run it to make sure it is okay. So this is for the first banana variety, all the 12, the scores on each of the first banana varieties. That is a green peel. These are the scores for ripe peel bananas. And then these are just on the first principal component. So on the first principal component, it seems to distinguish between these 2. These are green, right? So it gives a contrast between the green and the ripe, because you can see the green ones, they're all going in the opposite direction. The ripe ones are in the opposite direction. So these ones going to positive are these red and blue are the ripe varieties for both the peel and the pulp. So I don't know if this makes sense. These are 48 bars, 12 for each of the samples from each variety. So basically it's a bar plot of this first column. So it basically shows the length of this value, like this 0.12 should be the first one. They've been ordered correctly. It's 0.28. Just hold on. I may have plotted the. This is the second one. See, it's PC2. I think I changed this when I was experimenting. This should be the first principal component. So let's run that. Yeah, now this makes sense. So this first one was the one that's about 0.28, right? That's what appears here. Where is the scores? 0.28. The next one is 0.39, which is what appears roughly here. So this first one is a green peel variety, and this second one is a ripe peel. So this first component seems to distinguish between the peel and the pulp, because the pulp are in the opposite direction, the peel are in the positive direction. So the second one we saw distinguishes between what was PC2. Now this second one we saw is distinguishing between the ripe and green. The other one was between peel and pulp, because the ripes are in one direction. Is that correct? Let me just be sure. Yeah, the ripe varieties are in the positive direction. The green varieties are in the negative direction. So this sort of gives a contrast between those two. The second principal component. So ignore this first, this title. This title was because they initially I had the first principal component. So if you change this to PC2, maybe the title should also change. You could code it so that it does that automatically, but so I'll take it back to PC1. Is that making sense? So I'm trying to relate these figures to the actual values that we compute so that they're explanatory. So now we can do the plot of the first two principal components. So that is, if you go back to the scores, so we treat this as your X and this as your Y variable and plot X, Y versus X. You end up with this. So now within these first two principles, we have over 70% of the information we needed, and we can now see a very clear separation of the different flower varieties. You can see the, as indicated in the, if you go along the first principal component, it's not able to distinguish between these two. But on there are these ones which are on the left-hand side. It's red and is it purple? They are both pulp varieties. So it distinguishes between the pulp varieties, but it's not able to within, say, the, yes, what is this? This is peel. Yes, it distinguishes between peel and pulp. The peel are these ones on the left, or mostly the positive side, with a few negatives for this one. But the pulps are all on the negative side of a first principle component. So it's able to give the contrast between those two, pulp and the peel variety. The second principal component now distinguishes between the green and ripe. It gives that separation. So now, instead of using 13 variables, you're using only 2 variables, and you have almost 70% of the information contained. So when you're doing this for some professional work, you probably need to give better titles. You may need to format the graphs and make it better. This is just for educational purposes, so the labels are not as informative as they should be. So now suppose I have a new banana flower variety. We can take measurements on it. So these are the new values we obtained from that measurement. These are the values which have now been scaled already, right? They are not the original values. I created some values that look like the scaled values, not the original values. Because if you can look at these, the values are not so far apart because they've already been scaled. They are comparable. So this is a new set of measurements for a flower variety that we don't know, right? So I can project this new vector that contains my flower varieties, measurements from the new flower variety, just one sample, but with 13 measurements. I can project it onto this plot. So it may, wherever it lands, since I didn't know what it was, I'm more likely to classify as that variety where it has landed. So this is what this second line here does, that projection for us. You project here. I'm doing it manually, but I think there must be I think it's a transform. The transform method, it will do the same thing. This is the manual one where you tweak the components and you have the new data. You project it onto the first two. You can see I've only picked the first two components. So we're projecting it onto the first two. You can project it to all the 13, but then it won't be useful because you need only the first two. So I picked only the first two components and projected the new data onto the first two. You need only the first two because you're plotting the first two dimensions. So if you run this, you get a projection. It gives you a new point. So that this whole thing is replotting the old plot and then adding the new point. And then the new point landed here. This light blue is what? It's a green peel banana. So we suspect that flower must, if we didn't know what it was, if we had picked it from a crime scene somewhere and we've taken to forensics, they can now try to classify as this green peel variety. So this is not a very reliable classification technique, but in situations like this where the separation is very clear, it makes sense. But you can write some algorithm again similar to what we did for. So here is the Richman's way of projection. So you use PCA.transform, then you give it the new data and you reshape it. And if you print the projection, you will get the same values. Now, so these same values, we have printed the we had computed the projection earlier. So it was stored in this variable called projection. Then we have used the transform method to compute the projection as well. We just feed it with the new data and PCA was already trained earlier, so it can just predict using the new data. And you will see that there's the same values. They do the same thing. They have the same, look at this vector, this is the first one. This second one, we only pick the first two, so it's showing only the first two. You can see the first two here, they're equal to the first two here. So this will give me the vector, but this is projected to the whole, all the 13 components, and you can pick only the first two now from this first one. This will give you all the, to project it to the whole space, but you don't need all of it. So these are the projection that we did earlier. We specifically specified that we want only the first two projections. And you can see even from the output here, it has only the first two, but they're exactly the same as the first two of the one that's projected to the whole space. So what I'm trying to say is that this is a rich man's way of doing the projection, this transform. Once you had initiated this PCA and done the fitting, you form part to a new data set. So you can do this for more than one, like the same way we're doing for the digits last time. But now we're able to classify this one. Then this is the biplot. This is now the eigenvectors, but now plotted in 2 dimensions, projected onto the 2-dimensional space and labeled. So the and then we again, this you'll do this in machine learning, interpreting the biplot. There's another file for principal components. I thought we'd have to look at it. It has, in my opinion, it has a slightly more interesting topic. But if everyone is tired, we could stop there. I could share the file, then you go through it yourselves, plus the data. Any comments? So the advantage, the drawing this biplot, if you're working in R, drawing this biplot is quite easy. But in Python, there's no direct function for, or at least I've not seen one, where for drawing the biplot, you have to fight it out here and pull out the, so I don't want to go into these details, but this is a biplot. So essentially the smaller the angle between any two of these arrows, the more correlated those variables are, like the acidity, this pH or alkalinity, and the oil holding capacity seem to be very correlated. You could go back and check in the correlation. The ones that have large angles between them are not as correlated. I have not had any feedback on whether we should look at the other data set now.
We stop there.
So, so Ezra has asked something about linear data. Now, even for some, let's go back to the board. So you can have mostly, if your data was inside some shape like this, so I'm not able to draw. Suppose it was inside some. So in this case, it's difficult to find any direction that is of maximum variance. There are infinitely many. They all seem to, whichever direction you pick, they have the same variation. So in this case, PCA will not be able to assist because it might give equal variance to all the variables. So this is one case where PCA will not work. There's the other case where you have data that looks like this. So PCA worked very well on data that looks like this. It seems to have more variation concentrated in one direction. But now you might have two data sets, one data set that looks like a cross. So it basically it consists of two separate signals or populations, if you like. So in such a case, PCA gets confused also. It might give you a principal component in this direction, which doesn't seem to make sense for the data, and maybe another one in that direction. So this crisscrossing again means the data is mixed. So principal components may not work well for data that is shaped like this. So in such a case, you could use a technique called independent component analysis, or ICA. You'll be able to separate. Some books may call it a blind source separation. That will work. So PCA doesn't work for all the time, but if it doesn't work, also you'll be able to see it from your results. But for visualization purposes, you may try to use it anyway, but it may not pick up these patterns, for instance. So independent component analysis will be able to separate the signals. It will pick up this signal, and it will pick up this one as well, and give them to you separately. It can tell you, it can separate them. So though even this ICA, independent component analysis, still uses, or depending on what you're doing, you can, is still connected to singular value decomposition. Maybe I should, there's some application, but there's some calculations there that involve quite a bit of statistics. You have the kurtosis, you have, so you could follow this SVD-based method for separation. This works well for things like images. You can actually separate images. Methods for separation, this independent component analysis, but using statistical techniques. So mostly it works for data that where you can easily find the different directions. So like this one, it's very clear. You have one direction with a lot of variation. The next variation, the next one has less, and so on. So if you are in 3 dimensions, you look for the next smallest variation and so on. But it doesn't work for everything. It tries to pick these linear relationships. Then if you're trying to look for, the other thing PCA does not do is does not try to separate the different clusters. It just tries to find them if they exist. So there are other dimensionality reduction techniques, which we will not cover here. I think you will cover them in other classes, like TSNE. TSNE. This is a T-distributed stochastic neighborhood embedding. So this will be able to separate the data. The only problem is that now the distances between the points no longer make sense, but it finds your clusters for you. So you can't the distances now will no longer make sense. Points that were close in the original initial, that basically doesn't respect distances. Let me put it that way. You will cover this in the machine learning classes if you work. Then there's also the others as well. There's a uniform manifold UMAP. This uses some topology, uniform manifold approximation and projection or something like that. This also will try to separate the data. So there are other techniques you can use, but I think you will learn them in machine learning. So I don't know if that answers Ezra. Or he's left already? I know it's late. So so if there's anyone who is willing to hang on, I can go through the other file. It's just doing the same thing, but with a different data set, a much larger data set. So there we add one more trick to help us work better. We basically sample the data instead of working with the whole data set, because when you have such a large data set, the patterns are not easy to see if you work with a large data set. But if you take a sample, you might be able to pick out some patterns that otherwise you won't pick up if you use the whole data set. That's the only difference now with the other one, the one we are going to look at. And then it's more interesting because it's related to politics. So politics usually is an emotional issue and interesting for everyone. So once it comes up, not Kenyan politics though, it's Latin American. I think silence means you're tired, so we can leave it out, right? But I can share the file if you have the energy to look at it, you will do that. So this is a one we have just worked on in the chat. You will need a file. There's I'll send the file to the class rep. I'll send to Kibet. So Kibet will share it with you. I have the CSV file, the banana file, and the one for the Latin American politics. So the banana file, you will need to work on this. And remember, for you to use the file, you have to upload it. I showed you the uploading is done here. You see this folder. If you click on it, I'm disconnected now. So once you're reconnected, there's this button here. You click on it to upload. Then you just go and pick the file and drop it and upload direct. Don't upload it into any other folder. If it's right here, then the path is simply the file itself, the file name. You and you have to include the extension when you are importing. So Ezra, I don't know if your question is well answered, or this works well if we do a more detailed case and we actually test the PCA on data that is bad for it. So we are short of time, but it's a very rich topic. You can actually do a lot of experiments. So what you can do is you can try to generate data yourself if you know how to generate the data that looks. It's possible to easily generate data that looks like this. Another set that look like this. Then try to apply PCA to this data. You will see that it doesn't add a lot of value. Data that is circular like this. You can also generate data like this. And again, you will see that PCA will not be useful here because any two directions you pick here will be equally important. There's none that will give you more information than the other. So you will not be able to rank your variables after transformation. And I think there are some tests you can do to check this veracity. Again, here we are not interested in tests. I'm just interested in the linear algebra. The machine learning will teach you a lot of these things. The other concepts that I'm not covering. So, ladies and gentlemen, I think we can close the class. Everyone is too quiet. You must be waiting for this Mzee to stop talking. and wondering why he can't shut up and go to sleep. Am I right or am I right? I will share the recording also.